Good afternoon, everybody. So in the end of the last lecture, we were talking about what it means to be substitutable in Java. Right? So when you create a subclass in Java, you have to make sure that the subclass objects are substitutable for all of their superclass for all of the superclass types. So we're using this shape class to represent a hierarchy of two-dimensional shapes. Right? And we had a rectangle class and a square class that inherited from rectangle. Right? And we saw that this relationship here is problematic because of the following method. Right? So shape has a method called setDimensions. SetDimensions takes in a width and a height. And the method promises to change both the width and the height of the shape to the specified width and height. Right? It throws an exception if the width and height are illegal, so if they're out of the range. So for shapes, out of range means less than 1 or greater than 100. Right? And that method, so the contract or the specification for that method is quite important here. Right? It says that it will change both the width and the height of the shape to the specified dimensions. Right? And so if you try to extend square from rectangle, you end up with a problem because you can't implement a square where or it doesn't make sense to have a square where the width and height of the square are not equal. So if you try to do something like implement square and then override setDimensions so that it throws an exception if the width and height are not equal, you've done something wrong. Right? Now, the language doesn't care, right? So the compiler doesn't care about this. The compiler is perfectly happy accepting this code. Right? The problem is that setDimensions now throws an exception for values of width and height that are supposed to be legal according to the superclass contract for setDimensions. Right? And now suddenly you're in a situation where they're illegal in one of the subclasses. Right? I'll come back to this in a second, that line right there. Right? And so if you have a method like random scale, so random scale is a method that randomly changes the size of a shape. Right? It even checks to make sure that the new width and height are legal before calling setDimensions. Right? So whoever wrote random scale expects that the size of the shape will change at random, right? And it'll never throw an exception. As soon as you pass this method a square, right? So square is supposed to be substitutable for shape. Right? When you compute the new width and height, the width and height are probably not equal, almost certainly not equal. Right? Which means when you call setDimensions using S, right? Remember, it's the actual type of S that matters when you call setDimensions. Right? So in other words, if you pass it a square, it's the square version of setDimensions that gets called. And now suddenly, setDimensions throws an exception when it's not supposed to. Right? So if a subclass overrides a method, then it must accept all the parameter values that are accepted by its ancestor classes. Right? And so, oh, right. Because the square version of setDimensions does not accept all of the values that the shape version of setDimensions accepts, that causes a problem now in someone else's code. Notice how we implemented setDimensions here. So to actually change the width and height of the square, we call the superclass version of the method, because the superclass version of the method sets the width and height of the shape. Right? So it's often the case when, It's often the case when you're overriding a method, it becomes convenient to call the superclass version of the same method. Right? And that makes sense because when you're overriding a method, the method that you're overriding probably does something that you need it to do anyway. So you might as well call that method to get part of your work done, which is what I'm doing here. Right? So I'm calling the superclass version to actually change the width and height because it already does that for us. Right? So if you want to do that, just insert super in front of the method name. You can't write this, and you can't just leave off anything in front of it, right? So you can't just call setDimensions on its own, because then it calls itself, right? And this method isn't meant to be recursive. So if you write this.setDimensions, it becomes recursive. If you just write setDimensions, it becomes recursive. You don't want either of those, so you have to call the superclass version instead. When you use super to call the superclass version, it calls the version of the method from the immediate superclass. There is no way to go up more than one level in the hierarchy. right? So there's no way for me to call the shape version of set dimensions, for example, here. Okay, so if a method that you're overriding must accept all of the parameters or all of the values that the overridden version of the method accepts, does that mean that you can't change what values that the method accepts? And the answer is no. Right? So your subclass, you can't add or strengthen constraints on any parameter values in a method. Right? So square can't correctly add the constraint that the width and height must be the same. But you are allowed to remove or weaken constraints on the parameter methods, on the parameter values. Right? So for example, set dimensions throws an exception if the value for the width or height is outside the range 1 to 100. In rectangle, I can change the way that behaves. And I can say that rectangle set dimensions will accept any value for the width or height. Right? If the value is out of range, it will automatically move it to the appropriate side of the range. Right? So if you pass in a width that's negative, it changes the width to 1. If you pass in a height that's 105, it changes the height to 100. Right? But it doesn't throw an exception anymore. So in fact, the rectangle version of set dimensions will accept more values than the superclass version of the method will accept. Right? It's easy to implement. Right? So someone passes in a width. Right? You just make sure that the width is at least min length. Right? So the trick to do this is just to use max. Right? So the width is the maximum value of the width or the minimum length. Right? So if the width is less than the minimum length, then it automatically gets set to the minimum length. You do the same thing with the height. Right? And then you can play a similar trick for the other end of the range. Right? So if you want to make sure that the width is at most, max length, then you just use min. Right? So the width is the min of width and max length. Right? So that guarantees that it's always between min length and max length. And then just go ahead and set width and height. Right? So now we don't throw an exception if we're passed in a value that's less than 1 or greater than 100. Right? And this is perfectly fine because this version of set dimensions is still compatible or substitutable for the shape version of set dimensions. Right? So it doesn't mean that so if a method has preconditions, it doesn't mean that your inherited method has the exact same preconditions. Right? Okay, so what about the return value? Because methods also often return a value. So if a superclass method promises something about its return value, and a subclass overrides that method, then that method must ensure that the value also satisfies the promise of the superclass. So in other words, whatever the superclass version of the method is doing, the subclass version must also do the same, something similar. Right? So width and height both promise to return a value that's between 1 and 100. All right, so remember that, right? So they both promise to return a value that's between 1 and 100. So someone can take our shape class and say, well, I want to write this method that scales a shape so that its width is always equal to 1. Right? So if you have a width of 50, then it scales, and then it divides the width and height by 50 to get a value of 1. Right? Sorry, is that correct? We can say that so that its width is equal to 1. Something's wrong with this. Oh, I just realized there's something wrong with this method here. Hang on just a second here. So that its width is 1. This is problematic. Okay, I have to insert an if statement. Okay, so why might you do this? So this is called normalizing the width of the shape. It turns out there are people who study shapes, right, in general. This often happens in biology. So someone's looking at a slide or a picture of a specimen, and they have the outline of the specimen, and they want to know, is this thing similar to some other specimen? Right? And so they do what's called shape analysis on this. One of the steps in shape analysis is often normalizing the shape. So you change its width and height so that they're normalized, so 1. So you can normalize the width of the shape as long as its height is bigger than its width. So I'll have to deal with this in a second. Right? So you can do this. So basically what you're going to do is you're going to take the width, divide it by itself, and you're going to take the height and divide it by the width. Right? So let me just correct this method, because this doesn't always work. Right? So if the height of the shape is greater than the width, go ahead and do this. So if that is greater than or equal to that, okay, that's better. Okay, so if the height of the shape is greater than its width, then I can safely divide its height by the width, and that's still between 1 and 100, right? The width just becomes 1, and now I change the dimensions of the shape so that it has that width and height, right? And away you go, right? Obviously, if the height is less than the width, then we don't do anything, right? So it doesn't normalize the shape. You might want to throw an exception or something else there, but I'm just going to leave it the way it is. Okay, so if you look at that code, you can convince yourself that it is correct, right? So in other words, it really does scale the size of the shape so that its width is 1, right? The height and the width are both legal shape values, so they're still between 1 and 100. And so this method is correct, right? So anybody should be able to call normalized width and have this method work correctly. Okay, so suppose someone comes along and cooks up a class called vertical line, right? So a vertical line segment is straight up and down, so it has a width of 0, right? This is bad for 2 reasons, right? Number 1, you've broken an inherited class invariant, right? The shape class says the width of a shape is always always 1 or more, right? It also causes the width method to not return a value between 1 and 100. Right? So back here, right, if you pass in a vertical line, that width is 0. So you've now got a height, or some non-zero value divided by 0, right? And now you get positive infinity. Right? When you call set dimensions, throws an exception. It's easy to implement vline, right? So that's the problem with inheritance. It's really easy to do. There's no way that the compiler can check that if you're doing something incorrect. Right? So how do you implement vline? Well, you just call the superclass constructor, because that's what you always do in a constructor. Right? Then you set the width to 0. Right? For the width method, you always return 0. Right? This breaks the promise of the shape class method width, right? Which promises to return a value between 1 and 100. Right? So normalized width fails whenever you pass it a vertical line object. Right? So in other words, you've broken someone else's code, right? Whoever wrote this method, just by creating a new class. Right? There's no way for the creator of this method to know or to fix their method. Right? Because the fault isn't with their method, it's with whoever implemented the vertical line class. Right? But again, the compiler can't help you here. Right? And I don't know of any static analysis tools that can help you. So when you are implementing classes in a hierarchy and overriding methods, the responsibility is on the programmer to ensure that that their method is substitutable for the superclass version of the method. Right? Now, does that mean you have to return the same value that the superclass version of the method returns? The answer is no. Right? So you can return a different value in an overridden method, as long as that value satisfies whatever the overridden method says the return value should be. Right? So our area upper bound method, remember that method says returns the upper bound of the area of the shape. Right? If you made up a triangle class, you can compute the exact area of a triangle very easily. Right? And so you can change the way that area upper bound behaves. Right? It's just 1/2 the width times the height. Right? So that returns the exact area of the triangle. Right? The shape class contract says you should return an upper bound on the area. Right? But the exact area is also an upper bound on the area. Right? And so this is fine too. So you can in fact change the return value, and often it makes sense to do so. Okay, last one, I think. So there are methods that change the state of an object, right? So these are mutator methods. So if you have a mutator method in the superclass and it has it promises to change the state of an object in some particular way. You implement a subclass and override the method. Right? Then in the subclass, you must ensure that the overridden version of the method changes the object in a similar way. Right? Okay, so back to square. Right? So in square, we were throwing an exception in set dimensions when the height and width were different. Right? And so you go back and tell whoever implemented square, hey, you screwed this up. And they say, okay, I can fix it. Right? And so the way they fix it, and they say, oh, the reason this is broken is because I'm imposing this extra constraint. So what if I remove that constraint? Right? So in other words, right, they're going to do the following. Right? So you pass in the width and the height, and now they just ignore either the width or the height that's passed in. Right? Pick either one, it doesn't matter. Right? So here, they just use the width to change the size of this square. Right? Now it's still a square, because the length, the height, and the width of the square are the same, right? Set dimensions doesn't throw an exception anymore, so that's good, right? Our scale method doesn't throw an exception anymore, or random scale method doesn't throw an exception anymore, so that's good. But there's still a problem here, right? And the problem is, right, set dimensions in the superclass says, right, that it changes both the width and the height of the shape to the specified width and height, right? So describe a situation where code written in the contracts from the shape class fail when passed a square object, right? So anybody who writes a method using that takes in a shape, right, and relies on both the width and height of the shape to change according to the contract of set dimensions, right? When you pass it a square, you've now got a problem because square is ignoring one of the two dimensions that are passed in. And so it's easy to come up with situations where someone's code that appears correct now starts to fail when you give it a square. Right? So for example, someone's code might take in a width and a height and a shape, and they fit the shape into that width and height. Right? So they pick whatever's smaller. They pick whatever dimension is smaller, and then they scale the shape so that it fits into that shape. If you pass in a square, and you're ignoring one of the two dimensions in set dimensions, right? Now when you call their method, your square no longer fits into that width and height properly. Right? And then you can come up with lots of other examples that causes code written using the shape contracts to break, no longer, sorry. You can easily come up with methods that are written using the shape contracts that no longer work when you pass it a square. Was there a question back there? No? Okay. Oh, sorry, what's this? Oh, you can even go, so you can keep on trying, so whoever implemented square can keep on trying to fix their method, right? So here, set dimensions does nothing, right? So in other words, they always ignore the width and height. And instead of using set dimensions, you're now supposed to use set length in square, right? And so set length now does the correct thing, right? It changes the height and the width of the square so that they're the same, because length, it only uses the length, right? But now you've got a problem down here, right? So if set dimensions does nothing, it's now breaking the contract that it inherited from its superclass, right? It's no longer changing the width or the height of the square. So again, it's very easy to come up with situations where a method written using the shape contracts breaks when you pass it a square. All right, so that's all I want to say about inheritance in Java. There is a lot more to talk about, but I think that's sufficient for the purposes of a first Java course anyway. All right, any questions about inheritance in general? Okay, I guess there is one thing I can, oh no, we'll leave that for now. We'll come back to that later. So the final part of the course are Java generics. All right, so remember we had we had several different stack classes. One of them was a stack of ints. The rest were stacks of strings, right? So our int stack class, we implemented that using an array, right? So remember, we have an array of ints to hold the elements of the stack, right? We keep track of where is the top element in the array, and then we had push and pop, right? And the methods weren't terribly hard to implement. Right? Now, suppose I wanted a stack of strings instead, right? So this kind of sucks, right? So I have a stack of ints. I now want a stack of strings. And so if you didn't know about generics, right, you would say, well, you now have to come up with a separate class for strings, right? Then if you wanted a stack of doubles, you'd have to come up with another class for doubles, right? And if you wanted a class for something else, you'd have to make a separate class for that type of stack. That's not very sustainable, right? Okay, so is there another solution? So the solution before Java introduced generics is that, oh wait, before the introduction, so one solution would have been to make a new class, right? So when you do that, right, so if I make a string stack, right, and you look at the differences between a string stack and an int stack, you'll find very quickly that there are almost no differences at all. The name changes, the element type on the array changes, right? The parameter type for push changes, and the return type for pop changes. But almost nothing else changes, right? If you actually go and look inside the push method and the pop method, there's almost no change there too, right? The only thing that changes is that anywhere you said int, that now becomes string, right? Because your stack's now a stack of strings, right? So almost nothing changes. We can actually look at the pop method, right? So in pop, the only one thing that changes is the element type, right? The element type used to be an int, now it's a string, right? And that's it. So all that's changing are a bunch of type names. Right? In other words, instead of writing int, we're just writing string in a bunch of places. Right? And so wouldn't it be nice if the compiler could do that for us? Right? Because if it could, then the compiler can synthesize the new classes for us. Right? So this is exactly what Java generics are for. Java doesn't do it that way. Right? So Java does not make a new class where you replace string for int, right? C++ does it that way. So C++ has a mechanism called templates, where this is exactly what happens, right? The compiler synthesizes a new class, changes the types wherever it needs to, and now you have a second class that represent your other, so for your stack of strings. Okay, so there, before Java introduced generics, there was another solution. Right? And so what they did is say, well, instead of making a stack of int, why don't we make a stack of object instead? Right? Because object can hold any type in Java. So if I use a list to do this, right, instead of an array, I'm going to use a list. I'll show you how to use the array in a second. Right? So I'm going to use a list of object. Right? You push objects onto the stack, and you pop objects off the stack, right? There's no change compared to our original string stack class, right? Which also used a list, right? All that changed is object, right? So that's object instead of string, that's object instead of string, that's object instead of string, right? Again, almost no changes, right? The problem with this approach is that it's really inconvenient because everything's an object. So if you pop an element from the stack, right, you get back an object, right? Which means to use the element you just popped off the stack, you have to cast it to whatever type it really is. Right? So normally in Java, if you're using this type of stack, right, the programmer would be careful to only push elements of the same type onto the stack. Right? So if they wanted a stack of strings, they would make one of these. They would always push a string. Whenever they pop the stack, they would cast the return value to string and then use the string that comes out. Right? The problem is, like as follows. Right? So I'm going to make a string stack. I'll push some strings onto the stack. When I pop them off the stack, I probably want to cast it to string because I probably want to use the string for something like getting its uppercase version or something like that. Right? But you need the cast because pop returns an object. Right? It doesn't return a string. So the problem with this, so not only is it slightly inconvenient, right? You need the cast, right? But there's a more serious problem, right? You can push any reference onto a stack of objects, right? So I can make a stack that's only supposed to hold strings, right? There's nothing from stopping anybody from pushing some other type onto that stack. Right? The compiler can't help you here, right? Because the compiler is willing to accept any object and push that onto the stack. Right? And so because the compiler can't help you, there's no type safety here. Right? The compiler is the thing that normally ensures that types are compatible. So same example, right? I can make a string stack, push a bunch of strings, right? I can push a 1 onto the stack even though 1's not an object. Right? This works because the compiler converts the 1 to a big I integer object whose value is 1 and then pushes the integer reference onto the stack. You can push a stack onto the stack, you can push a date onto the stack, and you can push whatever else you want onto that stack. Right? And they all work. Now the problem becomes when you start to pop the stack, you don't know what's coming out. Right? So I would have to remember that a date comes out first, then a list comes out second, then an integer comes out third, and then strings come out fourth, fifth, and sixth. Right? That's really inconvenient. Now the fact that you can push any element type onto the stack, it now makes it impossible to write type-safe methods that operate on collections of objects. Right? All of these methods will compile cleanly, but they all fail at runtime. Right? So for example, here's a method called, in a class called sum and clear. So this thing is supposed to take in a stack of integers. Right? It's going to sum the values of the elements in the stack, removing all the elements from the stack. Right? So we'll start out with a sum of 0. While the stack is not empty, pop the stack. That returns an object, so I have to cast it to an integer. Right? And then add it to the sum. This thing here could overflow, but never mind. Right? When you're done, return the sum. So that stack is now empty. And it returns the sum of the elements on the stack. Right? The problem is that line right there. Right? Oh, sorry. Right? If I pass in a stack that's supposed to contain only ints, but one of them is not an int, right? That cast right there will fail. Right? So this method will fail with what's called the class cast exception when you try to cast that object to integer. Right? And so it's impossible to write a method that is safe, or that can safely be called for any stack object here. Right? What you really want is you want to call this method, and you want some way to say stack only contains ints. Right? So that's what Java generics are for. So generics in Java let you parameterize a class, interface, or method over types. In other words, you can pass in a type name as one of your quote-unquote variables for your class. Right? So instead of making an int stack and a string stack and a date stack and so on and so on and so forth, you can make one stack. Right? And you can say what is the element type. Right? And so the type here becomes a parameter for your class. Right? This says it's a stack of integer, that says it's a stack of string, that says it's a stack of date, and so on and so on and so forth. Right? The generic classes are type safe. Right? So if I write a method that takes in a stack of integer, it will only take in a stack of integer. Right? It won't accept a stack of string or a stack of date or a stack of anything else. All right, so how do you make one of these classes? Because we need to do this now. So when you make to create a generic class, you just have to specify some types. Right? And so the way you do that is class, name of the class, right? Angled brackets, right? And then your types separated by commas. Now the types here, these are just generic names, right? So they're not explicit types. So it's not like integer and then string and then double here, right? You give it some generic name, like T1 or T or E or something like that, right? And then inside your class, you just use your generic name for your type, right? So we'll see an example of that in just a second. Right? For your types, right, these are any, the type parameters when the user uses the class, these have to be reference types. Okay, so what should you use for your type names here? T1, T2, T3, and so on and so on and so forth. Right? So the recommendation is that you pick a very, very short name for your types. Right? So common type parameter names are E for element. Right? So lists, stacks, sets, maps, tend to use, sorry, list sets and maps tend to use E or T for their element, for their generic element name. Generic element type name, right? For a map, the key type is normally called K. The value type is normally called V. If you're writing a class that only accepts numbers, then N is a common type name. So let's cook up a very simple generic class example. Right? So we know that Java method only returns a single value, can only return a single value. Right? Same is true in C, but that's inconvenient in both languages. Right? So if you're looking for the maximum value in a list, it's often convenient to have both the maximum value and the location in the list where the maximum value occurs. Right? If you're in a language like Python or some other language that lets you return multiple values, right, you can return more than one value from the method. Right? The solution in Java, if you want to do this, is you just cook up a little generic class, and the generic class has 2 or more fields in it, and all the field types are generic. Right? So for example, that is a simple generic type that will let you return 2 values from a method, or pass 2 values to a method. Right? So our class is called pair. Right? It has 2 generic types, T1 and T2. Right? The field first, its type is T1. The field second, its type is T2. They're both public. So whoever makes a pair object can just write p.first and p.second to get the first and second values. To make one of these pair objects, is there an example here? Oh, there is, right? So to make one of these pair objects, right, it's easy. You just do new pair. Or in this case, you just write, that's not correct. Sorry, result equals new pair, like that. So here's a method max that finds, max, that finds the maximum element in T and also returns its index. Right? So if T's a list of integer, then my pair, the 2 types will be an integer and an integer. Right? It looks like the first element of my pair is going to be the maximum value. Is going to be the index of the maximum value. The second element is going to be the maximum value in the list. Right? Loop over the list. Right? Get each element of the list one at a time. Right? If that element is greater than the current maximum value, right, then result.first is equal to that index, and result.second is equal to the new maximum element. Right? Process all the elements in the list, and result now holds the index of the maximum element and the actual maximum element. Right? And away you go. Right? So there is where you specify the type, the actual types for your pair. Oh, I guess, so we can call the constructor here, right? Even though our class doesn't define one, right? Why can you call the constructor? Because the compiler makes one for us, right? We didn't define our own, so the compiler made a no argument constructor for us, right? Which lets us write new pair like that. Okay, so what about making a generic stack class? Right? So remember array stack, it used to be a stack of strings, I think. No, stack of ints, right? Stack of ints. So instead of an array of ints, right, I now want it to be an array of our generic element type. Right? So I'm going to turn our stack class into a generic stack class. Right? So put in the angled brackets. Right? Our stack holds elements of a single type, so I only need one type parameter here. Right? So I'm going to use E because this is a collection. And E makes sense for collections because it indicates that it's the element type. Right? Now this is what I want to write here. So I want to store my elements in an array of that element type. Right? This used to be an array of int, right? Now it's an array of some type E. Right? So that's what I would like to write. Right? Now the problem is as soon as you go to make a new array, right? So if you try to write new big E, right, and then square bracket, and some value here, the compiler now starts to complain. Right? So the compiler says, hey, so the compiler is perfectly happy with this. Right? So it doesn't complain at all about that. It's only there where it starts to complain, right? And so it complains, it gives you an error that says the compiler doesn't know how to make a generic array. Right? So remember, the compiler, all it sees is this type E, right? And it doesn't know what E is. So there's no way that it can actually make an array of that type because it doesn't know how big to make the array. It doesn't know how big E's are. Right? Okay, so in Java, you can't make an array of generic type, which is inconvenient. Right? The solution, though, is to borrow the solution from earlier. Right? If I can't make an array of type generic type E, why don't we make an array of big O object instead? Because I can put whatever I want into that array. Right? I still need a cast when I pop, but now the cast is inside the stack code. It's not inside the code that the user has to write. Right? So change that to big O object. Right? This is still E over here. Right? In the constructor, right? Now when you initialize your array, you just make an array of object. That's fine. Right? Now when you do this, there's something you have to be aware of. So when you're working with arrays in a generic class, there's something special about the ways arrays behave. So arrays in Java are said to be covariant. Right? So in other words, if I have an array of objects and I have an array of strings, then as far as the language is concerned, the array of strings is a subtype of the array of objects. Right? So in other words, an array of string is a subclass of an array of object. Right? And so basically any array of reference type inherits from big O object, an array of big O object. Right? And so that you have to be very careful with this because you can do all sorts of weird things. Right? So can I write the following? Right? So can I make an array of object? And can I store a reference to an array of integer in objs? Right? The answer is yes, you can. Right? Because an array of integer is a subclass of an array of object. Right? So array of integer is substitutable for array of object. So this compiles. Does that compile? Right? So the compiler says, well, what's objs? Right? Objs is an array of object. Right? Is hello a string? Is that substitutable for big O object? The answer is yes. So it lets you store a string in your array of object, in your array objs. Right? Even though its runtime type is integer. Right? So I've just stored a string in an array of integer. The compiler can't catch this error. Does it run cleanly? No, it doesn't run cleanly. Right? It doesn't. So when you try to run your program, when that line of code runs, that's when you get an error. Right? Now the runtime says, or the Java virtual machine says, you're trying to store a string in an array of integer, and I can't do that. Right? So now it barfs, right? Which is not nice. Right? You would like to catch this error at compile time. You don't want to catch this error at runtime. Generics don't work this way. Right? So generics are invariant. Right? So if I have a list of object and a list of string, there's no relationship between these two. Oh, sorry. There's no relationship between these two objects. Right? There's none. There's no inheritance. There's no aggregation, no composition, nothing. There's no relationship between a list of string and a list of object. Right? So list T1 is neither a subtype nor supertype of list T2, right? So no inheritance relationship exists here, which means I cannot substitute a list of string for a list of object, right? So if I try to do the following, right? Can I store an array list of integer in a list of object? The answer is no, I cannot, because array list integer is not substitutable for a list of object. If this was a list of integer, you could do that, right? Or if this was an array list of objects, you could do so. You could do it, right? But if the generic types are different, then these two things are no longer related in any way. Okay, so back to our stack class. Right? So for push and pop, there's almost no change. Right? So push, the only change that happens is right there. Right? So push changes because that used to be, that stack used to be a stack of int. It's now a stack of object. Well, that's it. That's the only change you need to make. Right? Nothing else here involves either ints or objects, so there's no necessary change here. Right? What about pop? So pop, there's only one change, and it's right here. So that used to be int element equals this stack, this top index. Right? The element now I want to be of type E. Right? Now remember, our stack is a stack of big O object. So I have to cast that to our generic type E. Right? The compiler will not complain very hard in this case. Right? It'll warn you that this is perhaps an unsafe cast. Right? But you know that the only way that you're adding elements to the stack is via push. Right? And push is always adding an element of type E. Right? So you know that whatever comes out of the array has type E. So you can, in fact, safely cast the result here. Right? And that's it. So notice the cast happens inside the push pop method now. It doesn't happen outside the pop method where our where our previous solution required. Right? And so converting that stack of converting that stack of int to a generic stack was almost trivial. Right? One change, second change, right? One change. So I guess that's technically a change up here. And one change here, and one change there, and add the generic type there. Right? So it's very easy to convert a non-generic class into a generic one in many cases. Not every case, but in many cases it is. Right? So now what about our interface? Because our interface is also for a stack of string. It's super easy to convert the interface to a generic interface. The stack of string interface to a generic interface as well. Right? There's the original. Right? So it takes in a string and a string. All you do, add the generic type here, change the element type here, and change the return type there, and you're done. Right? And so now you've got a fully generic stack interface, and you've got a fully generic stack implementation. Right? Finally, I guess the last thing we should need to do, we need to take our original array stack class and now say that it implements the stack interface. Right? And so that's easy to do too. It just implements stack E. Right? And now you're finally done. Right? Fully generic stack with probably, I don't know, 8 or 9 changes. And they're all small changes to the code. I guess that's a good place to stop. And we'll head over to the lab for those of you in the Tuesday lab. Otherwise, I guess I'll see the rest of you on Thursday.